Okay, it's time to start. Welcome back, everybody, to this new lecture. Today we are going to continue with the previous topic that we discussed on Tuesday about smoothing and mapping. Today it's going to be like how can we calculate things efficiently, right? So you will see later why this lecture is titled Square Root Smoothing and Mapping, or simply this kind of thing. Before we get into details, there's like some technical issues related to problem set 2. So there's some of you who are not submitting, right? You can either I think the best thing is if you are planning to use this one chance of being late, please inform the TAs, right? Because we are not sure now if it should be evaluated or we should just wait. Okay, so if you are in this kind of situation, please send an email. Ideally, everyone should have submitted by yesterday. If you submit it today, it's still fine. You have like, well, not that much penalty, but if you are planning to delay it 1 week, please tell us, because if not, we should be doing different things. Okay, so, well, about problem set 2, what is the general impression? Did you spend a lot of time, more time than what you thought? No, who spent more time than what you thought? Less time, you finish it before? You? No, you? Oh, okay. Okay, well, but still it's interesting because I think now everyone agrees. If we have finished the problem set 2, we have a better understanding actually what filtering means, right? Definitely localization problem. We've seen like 2 variants, one for the EKF, the other for the particle filters. You see things in action, right? You see actually what happens with a real observation model, well, whatever motion model you have, and well, that's basically the, well, I think an experience for you. Yes? I think next task compared to problem set 2 should be slightly easier. But there's only one way of knowing this, and it's after finishing it, right? So we are working on polishing some things before. Definitely problem set 3 was much harder than problem set 2 last year, but we are working on this. So the idea is that it should be equal or less complicated than problem set 2. Okay, by the way, yeah, problem set 3 is going to be available tomorrow, or yes, I think tomorrow, right? But it's going to be a variant of this environment that you have used. But now you will be implementing SAM, right? The algorithm that we explained yesterday, and well, you also are might be using some things of what we explained today. Okay, so, well, that's great. Definitely problem set 4, it's going to be much, much less. Right? We understand that as things are approaching to the end, well, all these deadlines just get accumulated. Just one remark. So this is a 6th credit course. It's valued equally as any other 6th credit course out there. So if you want to allocate points, it's up to you. But when you think about it, all 6th credit courses are valued the same. So just for you to think about it. Okay, so let's get into this. The summary of last lecture, which I think is probably one of the most important lectures that we are going to be presenting in this course, right? This new, well, not new paradigm, but this alternative approach to filtering. So we know a lot about filtering, but this new approach that is smoothing and mapping or calculating full trajectories is slightly different. It's actually equivalent for linear systems to the filtering techniques that we explained before, but the difference always comes for these nonlinear systems, right? So for nonlinear systems, there's like these peculiarities that I'm going to explain now that make this a little more convenient algorithm to use, right? Rather than starting with EKF or other kind of approaches. So if you remember last day, well, we defined our SLAM problem by a Bayesian network. If you remember, there's always like an observation, well, an action, an observation, right, pointing to a state, and then we propagate this to the next state, right? So this was a little tedious because you have all the time to write all these things, and it's not just for sketching the graphical model, right? What actually is happening here is that we are estimating the full, when we do inference, we are estimating the full distribution, right, of all variables, observed variables, latent variables, everything, right? So that came at a price. It's good for Kalman filter. We have discussed this, but maybe we can do slightly different. And in this case, it's true for the case of full SLAM. So if you don't take basically here this Markovian assumption that we were always taking, but we take the full trajectory, then we can express the same SLAM problem. And this is one of the first things that we derive with factor graphs, right? We did like some kind of crash introduction to factor graphs because I think not many of you have used them. But it's commonly used now in modern graphical, I mean, it's a very commonly used graphical model. In this case, we're also going to use it. If you remember, it looks like this. Now we have these two kind of nodes, right? We have the first node that belongs to the unknowns. In this case, I was plotting them as circles, right? So this is the variables that we want to calculate, right? And in this case, we were saying, okay, so we are not going to estimate the full distribution. This is just going to be variables that we are going to estimate. And then there's a second kind of nodes, like with points, right? And these points correspond to nodes that are modulating the distribution between these unknowns, right? If you see, they are always connected one to the other, so kind of nodes for unknowns and kind of knowns for distributions, they always connect each other. They never connect directly. So we never do this, right? That's not possible because then there's no distribution modulating. Well, there's not a distribution modulating the two unknowns or the two variables. Okay, so what we did is after some manipulations, this graphical model expressed the same joint distribution, right? So in this case, it's this joint distribution, right? And then the problem became a little different. Instead of just calculating this full distribution and then we calculate the posterior, right, conditioning by the observations, something like this. Instead of calculating this just by doing the proper Bayesian derivation, which is what we did instead is we calculated a maximum of this probability. In this case, these parameters are here just the unknowns. It happens to be x, like positions in the trajectory, and m is our map, right? Remember, it's the set of landmarks that we want to calculate. So it's the same problem, the same SLAM problem, as always. The only thing that has changed is that now we have a much better way of describing this. So if you use factor graphs and these distributions as we discussed last day, then this problem is exactly, or calculating the optimal set of parameters among the maximization of this joint probability is the same of minimizing a summation of what we call factors, right? So this came from the factor functions connecting, well, pair of unknowns. So at the end, it was just a long summatory. If you remember, inside there were like nonlinear terms, and what we were trying to do is always match like this observation with the expected observation that we should be seeing. There's like covariance. Remember now that the covariance that we are evaluating this against is not the full covariance. We are not taking into account x, landmarks, and then the observation. It's just whatever observation we have. So in this sense, it became a little simplified. And then this allows also to have like long chains, more suitable for optimization rather than propagating covariance all the time. Okay, so more or less clear this part, at least conceptually. Then later, who take a look at notes again, trying to follow these steps? Someone? We don't have a video yet because we had some problems with the network, but it should be today or tomorrow. Okay, so now that we are in this, we have exactly this minimization with a summation of squared terms, if you want. We did some approximations, as always, linearization, and then, well, we did some manipulations with the covariances. And then it turns out that this problem is actually just a linear least square problem, right? So in this case, here, remember that deltas was this update. X0 is our previous solution. This is the new solution. And then we always calculate the update, right? Because, well, for this way of describing the problem, it's not possible to obtain directly X, right? But still, that's fine. We just update it. That's actually common, right, for many iterative methods. So they do the kind of the same thing. And then the minimization was like after grouping some terms, stacking vectors, and this delta is basically the stack vectors of all your trajectory and landmarks. We got something as this, right? Very compact, well-defined. You remember this A matrix. Okay, so yesterday, well, Tuesday, the class was a little intense on all these details, but I'm going to repeat this idea, which is, I think, very important. You can revisit later the details on how to derive all these things, but the important thing is that we got from this initial description of our problem, which is a joint distribution, right, into a least square problems, right? And we are not changing anything. We are not doing any assumption except linearizing, right, the nonlinear functions. But these two problems were equivalent. And actually, this will give us like some advantages when we solve things. Okay, so the A matrix also could be understood as an adjacency matrix, because here we were just, on this matrix, terms that are not zero correspond to actually real edges in our graph. But if you don't want to follow this, it's fine. We can always use the observation function and transition function that we were using before. But in essence, the adjacency matrix looked something like this. We had here a bunch of factors that depend on the odometry, right? And then here we have like something like this. Here this is X, this is M. Right, so number of columns corresponds to the variables, and here what we have is observations, well, Z in general and U. Right, and here the second kind of observations, well, I'm just going to here write observations, but in general we have this, right? So rows, each of them correspond to observation in general, could be odometry, could be observation of landmark, whatever function you have. Technically speaking, so the question is, what's the difference between observation and odometry? Technically speaking, the difference is that odometry changes the state of the world, right? So if you remember the transition function, it depends on a previous state, and then what you get is a new state, right? While observations in general are just a function, right? Given your state, you observe some observation, which can be whatever, right? So in this case, there's no change but you can think about them also as observations, right, this odometry. So if you want, you can call all of them observations in general. It's basically things that you are measuring, right? But this distinction is, well, a little detail, very subtle, but it's just this. One is changing the state. The other is just giving you like an observation from another kind of mean, like this landmark. This is how I'm observing it. Okay, so we have all these terms. On the observation function, it always depends on a state. So these are, if you remember, Jacobians with respect to, well, positions. And then here we had like Jacobians with respect to landmarks. So in this case, there's not, it could be any landmark that you observe at any time, right? So this is the structure of the problem a little, right? Actually, in problem set 3, you are going to implement the adjacency matrix. You are going to build an adjacency matrix for a problem, right? So you will see very clearly then what is exactly what part. I remember from last year, so students were saying, oh yeah, the adjacency matrix looks easy, right? There's nothing really complicated there. But then there's a lot of little details that you need to take into account, right? So I would suggest you to go again on the previous lecture. You have all notes. You also have the paper. And then you will see like, I don't know, like the square root, transpose, covariances pre-multiplying, right? Or exactly what is this Jacobian? How are you evaluating? These kind of little things on the implementation might be a little tricky. So just be aware of this. It looks easy. Conceptually, it's very easy. It's some sort of adjacency matrix if you want to take it from the graph perspective. But, well, there's going to be little details. Okay, so here we have this, the adjacency matrix. And after we have this, how can we solve this? So our first guess was, well, we were just doing a derivation, right? We do the derivation of this cost function, if you want. And then the result is that we want, if mean, well, then this should hold, right? So AD. And then it's very convenient for us because now it's not really an optimization problem, but this problem became just solving a linear system, right? It's overdetermined because if you remember well, or if you take a look at this, maybe the number of columns is not the same as the number of rows, or saying this another way, the number of variables here that we want to estimate might be smaller than the number of observations, right? So that makes our problem overdetermined. But this is normal because we have said that actually we get more certainty as we reobserve things, right? So this kind of reobservation, basically the result in terms of dimensions in this matrix is that this is going to be rectangular matrix. Okay, so, and then what we did is, what we explained is that we are going to use iterative methods. But the very interesting thing is that we never marginalize information. We never do the correction step as we were doing before. There's always a way for us to relinearize A, right? And we are not adding information to the system. I'm going to write it this way. And this, actually, it's one of the advantages of this approach, because if we always relinearize and we just assume that we have a previous point, a previous solution, right? Remember x0, right? So it was whatever x plus delta. Or the other way around, I don't remember now on the signs, but if you have something like this, basically linearization, it's always very close to the optimum, right? And as you approach, it's going to be better and better. And there's no need for you to do you are not accumulating linearization error, which, if you remember, was happening on EKF, right? That's why we propose this iterative EKF and then, well, these other approaches. So here, you always relinearize. Linearize, it's cheap, right? If you have a closed form, evaluating this is cheap. And doing linearization errors, that's very complicated. Okay, so this was last lecture, more or less. Yes? What is what? This? While solving. Okay, so before we start, is this part clear? I mean, we cannot really continue if there's still like any doubt, but I hope I have convinced you after many, many discussions on this topic that we are actually solving the full slam problem, right? It's simply a different way of doing it. No? You don't see this clear? No? Okay. Yes.
So what conceptually mean by the minimum added information? Actually, when we symmetrically
So, well, here the term information might not be very well used. I would say that it's not in the sense that information comes from observations and that's how we are at information. All that is there. But what I mean is error from linearization. Exactly, because if you remember, for instance, when we do the update of this kind of matrices, this is linear, this is a linearized Jacobian, and if you do this iteratively, then basically you're accumulating error because this linearization point is going to be changing, right? And what you have calculated as your posterior distribution, when you keep doing things on filtering, there's no way for undoing it. While in this sense, there's always linearizing, right? So we are always on our best estimate of where we could be. The contents of the matrix say the adjacency matrix. Here, well, what we have is all these factors that belong to the odometry. So if you remember, it was something like minus the identity, and then there was the Jacobian. Right, so this was terms that we are adding here, like here and here. And basically, all the other derivatives, all the other Jacobians with respect to other things doesn't matter. Because if you see Jacobian only depends on state A-1 and state T. Well, state I, right? That's why we have also an identity, right? Although this might be trivial, it's still important. Identity is not null matrix. But actually, this comes from here. So if you move this to the other side, you have a minus XY, right? Okay, let me put it this way. So this equals 0, right? So this is where all these Jacobians come from, and then you can do the same thing from here. So in this case, in this you have the Jacobian with respect to x, right? That's what I'm writing here. So this is the one that comes here. And then here, what we had is these Jacobians that I think I was using. Okay, I'm going to use a different color. Jacobian of k of, now this is Jacobian with respect to landmark, right? And these were here. So if you see, this thing matches, because here on the rows, you have whatever observation you have, k observation. But on the column, what you have is the unknown variable. So here, in this case, this Jacobian is with respect to landmarks. So it makes sense. Here we have landmarks. That's why this thing is here in the matrix. And here is the same for positions, right, or the x variables. Here, this Jacobian is with respect to the x I variable. And then all the others are simply 0, right? Okay, so with this matrix, actually, we define completely the problem. That's also a very interesting fact. Let's talk now about new concepts, right? I'm going to talk now about the chi-square error, actually, that we are doing. If you remember from that lecture on data association, I think lecture 9, we were discussing that actually we made use of the chi-square test, right? So it was just the exponent, and from this we selected a confidence level. We choose what was the dimensionality, and with this we could test hypotheses. But actually it's also a good way to measure the error, right? And basically at the end this is the error. If everything goes well, all these factors here match perfectly, right? And if they are matching perfectly, that means that we will have a chi-square error of 0, right? Every residual will be exactly what you expect. You are seeing what you should be seeing, right? So you are here, your observation is telling you that there's a landmark just in front of you, and the observation is just that, whatever is in front of you. But there's always some error, right? And basically, when you solve all this summation of residuals, although you optimize to get the minimum cost of this, there's always going to be like some value. And actually, this is the error, right? So we had all these summations. Now we discussed that actually you can put this way, right? And then if this thing has converged, right, that means that these updates that we are doing on, okay, I'm going to write it better. Right? So if this has converged, that means that we cannot improve anymore our solution, right? We are already there. This is, this is a stationary point. Basically, we are not going to move from there. So these updates from our x whatever, the deltas are just going to be saying, look, you stay here. You are not going to move. The optimization is not going to tell you it's not going to move. So then this error, the whole error that we are doing, it might not be 0. This is simply an optimum. It's just going to be b, right? Because here delta is 0, right? So what we have is the square, the norm of b, right? So this is it. This is useful to see exactly how well you are doing. You are calculating your solution. You say, awesome, I got minimum, but how good is this minimum, right? Are we matching really like all the observations or not? So you can test it this way. Just come here. If you want, you can reevaluate your solution and then calculate this norm of B. And this is going to tell you like how confident you should be doing. You can also take a look at chi-square tables or whatever you want, right? Because at the end, what we said is that this is going to be looking like a joint Gaussian distribution, right, after all these manipulations. So easy to calculate chi-square, and this is exactly this, right? B transpose multiply B. No, I didn't derive this. I use this, so you need to take this as a fact, that the exponent, right? All these summations here, all the square parts, are just the exponent of your probability, right? If you take the summation of all these, at the end these are residuals squared, this is going to be the same as a chi-squared variable here. No, here you don't have an hypothesis. You just have a measure of your error. So if you ever want to say, okay, how good your solution is, this is a way of describing it. You could also be, okay, you can be comparing with ground truth, and then we have another kind of metrics. But just by itself, this is telling you without any kind of external help how well you are matching everything. right? Basically, say. Okay, so how well can you perform? Can you know how well you are performing? Yes, you can, because this chi-square actually has like some dimensionality, right? This is the dimensionality of your state variables, and then it's going to have like whatever confidence you want. You are just going to see like for this dimensionality, what is the confidence level, right, that you should be seeing, and maybe, I don't know, it's 90%. Fine, awesome. Maybe it's 10%. Oh, then you are doing bad, but it depends on the table, right? But still, just as a measure by itself, it's a good measure. If you want to measure, if you want to have like a way for convergence, right? This is another metric that you could be using. You measure the chi-square error, and when this thing doesn't decrease anymore, up to whatever tolerance level you set, then your iterative estimation is over, is finished. Okay, so, well, this is a little more for you to use if you want, but doesn't change much. Let's discuss now another interesting part, which is about the information matrix. Oops. If you remember last lecture, what I said is that, well, you have your adjacency matrix, right? And in fact, if you multiply the adjacency matrix this way, what you get is the information matrix, right? So that's going to be useful, but we still need to show this, right? So I'm just going to show it very quickly. So why do we want this? Because at the end, we also want distributions, right? And basically, this is going to give like the covariance of this posterior distribution. This is going to be useful. Although what we do is maximizing. Actually, there's going to be a distribution after doing all this calculation of the joint probability. Okay, so SAM is a map estimator. Okay, just as a reminder, we obtain this from this maximization of the joint probability. You will see in a moment exactly where we want to get, right? And then what we applied is minus logarithms and linearization. And then what we get is that this problem actually is equivalent to minimization, right? This is the same thing that I just said before, but there's going to be a little difference, because you remember from lecture 3, right, what happens when we complete this square. We had a joint Gaussian, which at the end, yes, it was a probability, but then we were always working with exponents, right? So the same thing happens here. What we have is a bunch of exponents. All of them can be expressing also a joint Gaussian distribution. So let's see exactly what is the covariance of this. So all factors express a distribution. Okay, so we have this form. This is what we want to calculate. Actually, we can rewrite this in the following way. I'm just going to expand until we get something that looks like a Gaussian, right? And it should be ringing some bells at some point, right? If we follow lecture 3. So we have this, right? This is just the norm, but written in vectorial form. Remember, these are just vectors, right? So we are just multiplying transpose vector by this vector, and then we have a real number. We can expand actually each of these terms. right? So we are going to have something like this, right? So this is for deltas. The same goes for delta with B. The same goes for B with delta, yeah. And then finally we have BT, B. Since these are real numbers, we can just transpose, and the transpose of a real number is the same real number, right? There's nothing here happening, so you can group these things. And then, no, but we don't need this. Let me just write this. So if we write B to be equal to this adjacency matrix multiplied by a mean, and what this mean is, we'll see. But just let's do this little change of variables. Then what we get is, I mean, this thing doesn't get changed. Here I'm just grouping this, knowing that this is a real number, so I'm just transposing this, so we have like the two things, these two things are the same. And now what I'm substituting is B to be equal to A multiplied by a mean. And then if we substitute here on B, we are going to have the same thing. Okay, so this is what we have obtained. Does this look familiar? Like, would you say that this is the same thing that we have in joint Gaussian distributions, right? The same kind of exponent? No? Okay, let me group a little more these terms, right? So what I'm going to do now is see that we are multiplying all these vectors always by the same matrix here, right? So now I'm going to do this. Okay, and this is the same. So does this look now like a Gaussian to you? Kind of, right? So if this is a Gaussian here, this will be our variable, this is our mean. We just happen to say, okay, this is whatever mean. Doesn't really matter for now. We could be calculating this, actually. But the important thing is that because we had this factorization, these matrices here are the same. And then, in fact, this could also be explained as a joint Gaussian, right? And then the covariant, well, not the covariance, in this case, the information form, the information matrix would be this AT multiplied by A. So we've seen that just because we did all these extra manipulations here, remember that we have covariances, well, the square root of covariances transpose and all these things. At the end, what we get is that all this was actually a joint Gaussian distribution, right? In information form, things are a little different than in covariance form. So remember, in covariance form, it's very easy to marginalize. You just take a block of whatever you want to. But it's a little more complicated to condition. Here, in the information form, conditioning it's a little easier. And actually, what conditioning is add new information. And this is what we are doing all the time. So all this, if you think about it, this is just a big summation of terms. If you want to add a new term, you just add that term. There's no need to add like a draw factors for all of them. You just add those that are affecting this part, right? So the information matrix, if you add information, that means you are adding observations or you are just conditioning with respect to these new observations. It's very easy, right? So that's why we can build the covariance, the information form this way. Now, what happens with the covariance? So the covariance is going to be a little more tricky. But everyone agrees now that this, if we expand like all these terms to be a least square problem, then at the end, you can also explain this as a joint Gaussian distribution. And the information form is going to be this, right? So it's great. Our matrix that we have calculated before, we know that it's also going to be useful if we need like a covariance, right, of our distribution. We were doing max, but it turns out that this is actually a posterior distribution as well. And well, it's not clear exactly what is this delta minus mu, but you know that delta is this, right? So our variable minus our current solution that we have calculated, and we are always trying to increment this to be as close as possible, right, to the optimum. So, okay, good? Not good. Yes. So you have B. B is known. A is known, right? And then basically what you need is, you just need to derive it. It's still a little, okay, so I think, yes, you need to do a leap of faith here because there's no inverse of this matrix, but if you do the pseudo inverse to get this, you should get to the same spot. If you do the other way around, instead of just saying that B equals this, you can also start by what we did with the completing the square. So if you remember, we had this for completing the square. We had like a form, square with respect to the variable. So that means that whatever happens later, we are just going to make it such that this matrix is then later multiplied in other places. And the only way that this can happen is that if your mean equals this. Right, so I put this like a little leap of faith, but when we're completing the square, does everybody remember this? What we were saying is, look, the covariance is going to look like this because x should be multiplied by your covariance, and then whatever comes later, we are going to adjust it until we get a kind of Gaussian form. Right, so it turns out that everything matches perfectly here. To select the full square, what does this mean exactly? Yes, exactly. So we don't need to complete this square here. It falls very naturally because every term just happens to be like already multiplied by these terms here. So you see here, and we don't need to make up like any term. So before, remember, we were also adding like a constant factor, but here in this case, you don't have to do that. Right, so, okay, then the question would be, does this mu actually exist? Is this meaningful? But I think for now, yes, let's just do this simple change of variables. For this explanation, I think that was enough. If it's not good enough, then let's discuss later. But I think you need more math. But still, it's true. I'm not making up anything. Okay, everybody agrees on this, right? We have information form. Yes? Thumbs up? No? Thumbs up. Okay, good. So this is going to be an important result because then later we can justify it, right, that actually our solution is a distribution as well. Okay, let's get back to the normal equation as we were defining last day. So the problem was we want to solve this, right, for the minimization problem. And then the normal equation, it's commonly known as this. We pre-multiply things by the A transpose. Again, why? Well, we'll see later. But you can do this. You pre-multiply both sides. And then what we have here is no matter what is the size of A, here this is going to be a square matrix. And basically, we can invert, right, a square matrix. And we also discussed that this way of inverting, it's called pseudo-inverse. It's not really a proper inverse, but it kind of looks like this. Because effectively, yes, what we are doing here is this, right? Pseudo-inverse, right? So we have here this form. Okay, so what's the problem? What's the problem of this? There's always a problem, right, in this class? That's good, because we always solve it, kind of. No? We don't solve it? Okay. We try. So the intuition is that if you want to solve this just by brute force, fine. You go there, then you invert this matrix, you multiply by this, and then you have your solution. That's it. Problem solved. Now, the complexity actually of this depends on the square of the number of variables, right? So that might be a little intense. And what we have discussed is that A is sparse, right? Sparse means that there's many zero elements, right? Enough just to represent this matrix, not maybe with a kind of block memory of all elements, but using a different representation. This also gives a lot of advantages when you calculate like some matrix factorizations. Okay, so the idea is simple. We have this is the earliest way of solving it. You can even, actually in problem set 3, you are going to be asked just to do this. Go there, calculate the inverse, run away. But there's better ways, and this is especially true. Imagine instead of having like 100 terms in your trajectory, you have 10,000. Well, 10,000 probably it's not going to be that good, right? Even just to storing this thing in memory, it's going to be like a little intense. So you have a 10,000 by 10,000 matrix. So here, sparsity will give us like really an edge on how we solve this. And this is really great advantage because before we were always discussing on covariances. And covariances are always dense. We always have these little cross terms that are just a result of calculating, well, of just propagating. You remember covariances, how they were growing. We were discussing for EKF slam. Okay, so now we have this cross term that depends on this. And then there was actually not many parts where cross terms were zero, right? Unless we were doing initial conditions or other things. So let's exploit this sparsity. Right, so for this we will need like some linear algebra, but I think this will be better. Everyone is convinced that we want to explore this a little more. And actually the adjacency matrix are almost empty. We always have like kind of long chains and then some observations here and there, but it's never a fully connected graph. Our trajectories are never always fully connected. If it was fully connected, then you should be using just this. But since they are not, you keep moving, maybe you observe a thing, you observe it again. This changes the structure of the problem, right? And there's a sparsity in this kind of a structure. So let's use this. Okay, so this might look familiar, but again, we are going to be using Cholesky. Oops. So what do we know? We have an information matrix. We know that this information matrix equals this, right? And then what do we know about covariances matrices and information matrices? What are the two main properties of these matrices? Symmetric is one of them, and positive definite, right? So that's great. That means that we are suitable for using the Cholesky factorization, right? And in this case, we know that although this is like this, these two matrices are going to be different. So we can factorize into two equal lower triangular matrices, something like this, and then the transpose is going to be something like this. Or we can factorize this into upper triangular matrices, right? And in this case, it's going to be the same, but it's simply one, the transpose of the other. So you could have like any choice. This factorization is very efficient, right? But it needs positive definite matrices, right? So we don't care because our problem is like this. If not, okay, maybe there are other factorizations, right? Like LU or something like this. But for this problem on information, we have already discussed that Cholesky is a great choice, right? Okay, so then what do? We have this. This is the information. And this is, well, our new residual. What we do here is just Cholesky of this, and then we are going to have an upper triangular matrix transpose and a triangular matrix multiplied by this unknown, this vector of unknowns, right? And then, well, this vector, some values. Okay, so this is what it's called square root sum. It comes from here, right? So Cholesky can be understood as a way of doing the square root of a matrix, kind of, right? So we have here a matrix that equals two things that are the same, right? So that's kind of a square root. And actually this turned out to be a very efficient way of filtering and doing a state estimation like quite some years ago. And well, here in this case, the authors, you have the paper in Canvas, proposed to use the square root method here for doing this very efficient way of calculating the solution here. So why is this efficient? Let's go a little deeper into this, right? We have two triangular matrices, right? So what we can do is solve this in two steps. Is anyone familiar how you solve this? No? No. QR will come later, but no. Let me rephrase my question again. Once we have a factorization like this, these are triangular matrix, something like this, right? This is RT. So how we solve a linear system with this kind of matrices? You're familiar, right? So this is, everyone is familiar. Okay. You were just pretending. Okay, I'm going to explain it anyway in case that. Okay, so what we are going to define here, it's an intermediate variable, right? And this intermediate variable should be this, right? In this case, oops. In this case, what I'm writing it this, right? So this is y, right? I'm just here substituting this. And then there's going to be another term that we need to solve after first solution, which is going to be this, right? So, and why is this efficient, right? So basically, this is called back-substitution. Let's go to this R matrix. We have here this kind of matrix. We have here like a vector, and then we have another vector. Okay? And all these things are zeros, right? All these things that are not much like these are zeros. So in fact, we have something that it's going to be very easy to calculate because, for instance, for solving the first equation here, what do we have? We just have one variable. We have a lot of zeros. So imagine here, we have a variable. A lot of zeros multiplying this, and this should be equal to this term here. So at the end here, we don't need any other value here for solving this first variable. We just need this value and the value here. And if you do this, well, actually this will be a forward substitution. But here we have this is transpose. This is the upper triangular, right? And this is going to be back substitution because we start by the end, right? So very similar to Gauss elimination, but a little more properly. Let me write now an example of this. Very small numerical example. I think many of you are using this like on the background when you are like solving a linear system, right, in MATLAB or Python. It's already doing this. And this is a topic of previous course, right, that you did in numerical linear algebra. So, okay, well, in case that someone didn't take this course, it's still fine. We can catch up. Okay, so this example, right? I'm going to write like a lower triangular matrix, something like this. I think numbers are just made up, just for me to calculate things easily. Right, so this will be our R matrix. This is our vector, and then this we have here that this should be equal to whatever values we have here. Right? So this is what I was talking about. We have, three equations, three variables. We want to solve them. Which one is the first one that you should start? Which one is the easiest one? We start here, right? So we solve this, multiply this by this, and then what we are going to have is that our second variable is going to be multiplied by 0, our third variable is going to be multiplied by 0, and then what we have is that y1 equals 2. Right? So this is awesome. If you can factorize things this way, it's going to save us a lot of time. Again, so for those that you already know, you know that this is a very common thing. But in case you don't, well, here I'm showing it. And well, the same happens for the second equation. That's what we are calling this forward substitution. Here, now we have the value of we have the, for the second one. We have the value of I1, right? So we simply substitute here 5 is multiplying I1, and I1 in this case is 2, Y1. And then we have 7 multiplying Y2, right? And then we have 0. And this should be equal to 5, right? So then it's the same thing. We just have one variable, and what it was a linear system just becomes like forward substitution of all these things. You can imagine you keep doing this. For 3 variables, it's fine. Actually, you can solve this in many ways. You can invert, but if you had like thousands of them, this is going to be very convenient, right? So, well, now you know what is behind this, why we want actually to factorize this matrix into a Cholesky factorization, and how this is going to help us. So this is 2 steps, forward substitution and backward substitution. Yeah, one question. Can we always find a solution? Yeah, that's a very good point. So if there's not a solution, it's because, let's say that your matrix is not well defined. It's rank deficient. And Cholesky is taking care of that, because Cholesky only factorizes positive definite matrices, not semi-positive. So if you try Cholesky of your rank deficient matrix, is going to tell you, look, I'm not going to do it. Right? So yes, it's true that you might be asking, okay, is this solution well defined? But in fact, it is, right? If the information matrix is well defined. If it's rank deficient, that means that you are doing something wrong when you are adding information, right? It means that you are trying to optimize or estimate some variables that you haven't observed. So how to do that? You don't know. What this means in terms of linear algebra, that your matrix is going to be rank deficient. You don't have there like basically a dimension where you should be improving. So usually, yes, if we add enough observations on our observation the right way, this matrix, this information matrix should be positive definite. Okay, good point. So well, I think I don't have to write this. Let's do a little, comparison. So you have this Jupyter notebook in Canvas, if you want to use. I'm going to do a break after we finish this. So what we were trying to do is just illustrate all these things, right? Because I can start talking about Cholesky and all these things, and at the end it's just going to be a couple of equations. So what we did for this lecture is you have this. You can play around with this. Here what I'm doing is I'm pretending that I have an adjacency matrix. This can also be useful for you for problem set 3, unfortunately, what I'm doing here is my Jacobians are random numbers. So it's kind of a very stupid system. But still, imagine instead of having a block matrix corresponding to this, what I have is just a random number, right? But the structure is gonna look similar. So here we do, we do some things here, and this is how this adjacency matrix should look like. Right? You can play around, you can actually change the number of variables, you can change the number of observations, you can change, I think you can change, many other things. So you can play around, and this is just gonna start creating like random observations. From this structure, what can we say? This belongs to, okay, so in this axis, these observations, these are so you are right. These factors here in this part, number of columns, this belongs to x. This is the trajectory. So all these and number of rows, this corresponds to the observations, or in this case, odometry. So these are all the odometry factors that we add. Remember that it has like some kind of this structure. Here it's one element, one next to the other. Here we'll have x. And here we have all our landmarks. So for propagating the system, landmarks are not affecting at all, right? So that's why we don't have here anything. Again, it's kind of randomly generated, but it should look like this in your problem set as well. And then we come to the next kind of observations, which are just observing landmarks. In this case, we'll have the same pair. So there's from any position, and here there's continuity because I don't know, the sequence of observations is order in time, for whatever reason. We always see like one position in our trajectory, this one, and then we see a landmark, right? And this happens every time that we have an observation. So all these things that look like a little scatter actually are, each of them is a row and corresponds to an observation, right? So looks reasonable, looks like an adjacency matrix as we have described. You can play around with this, so you have this in Canvas. And then what happens is, let me show, so what we do. If you do the adjacency if you calculate the adjacency matrix transpose by adjacency, the information form, you get something like this. This is just for this particular structure of the problem. So when we have like odometry and then observations, the information matrix is going to look like this. We have a strong diagonal. It's a good sign. So probably it's not going to be rank deficient. Here we just have like, well, after doing this, just a diagonal matrix or block diagonal matrix. Because why? Landmarks are not really correlated between them. We never have. So this is things for you to think. We never have here like an observation of two landmarks, as we have described it, right? So that means that if you're not observing directly two landmarks, although there's a neighbor that is observing one maybe through the other, since we never calculate the posterior, as EKF would be doing, we never add here cross terms. If we were doing like EKF, like full vector, then here we'll see like slowly where we add like information parts here. Right? This is true when you marginalize. So the last question is about cross terms. In this term, cross information terms regarding the landmarks. So this is a block diagonal matrix. There's no cross terms between them because we never marginalize our information. We always keep the full trajectory. And then we linearize. So the advantage of this is that this information matrix stays sparse, right? Even after many iterations of iterative solving of your problem, even after increasing the problem, it's always going to keep this sparse structure. Here we have all these cross terms. This makes sense, right? Because here, basically, landmarks are related to positions, right? We are observing landmarks from some positions. And here what we have, it's block tree diagonal matrix. It's not really block diagonal, but here we have terms, and it's because, well, we have these two things, right? It was Jacobian, and next another Jacobian, right? But okay, you can think about this almost as a almost diagonal thing, block diagonal thing, and then here there are no cross terms. So the same is true for propagation. Does it make sense to have like a cross term here when you are propagating? If our propagation function only takes into account previous time step, current time step, and your observation, right? So this is just checking of, yeah, things look good. Okay, you can think a little more. You can try to look for things. This is symmetric. Yeah, well, that's hard to see. I don't see it. I see points that are symmetric, but this is not a property, and this is just because how we are building this matrix, right, with a kind of square form of ATA. That's, I mean, it's going to look like this. And then here comes the interesting part that I want to show. So this is the inverse. It's not a black hole, it's blue. But still, it looks pretty bad, right? And the problem here is that although in information form we don't have cross terms, that's not true for the cross terms in the covariant form, right? So in information form, these things have like zeros, but if we do the inverse, actually all of them are related, right? And that's why doing the inverse, it's never a good idea. So it's expensive, and not just that, but actually you are going to have here a lot of things that before were zero, but before you do the inverse now are going to be very small. They are still non-zero, right? But they are still, well, basically we'll have a dense matrix after doing this. But these cross terms should be very small, should be different. Definitely they don't have to be zero. It's only the information form. So when you do the inverse, then this is the price to pay. So that's why we don't really want to do the inverse, right? This is something you can do. It's always available. But with this, we break sparsity. We absolutely break it. Okay, so then what can we do? Right, so this is the first approach. Just initial Cholesky with any. Here, you can play around also with this Jupyter notebook. Well, here I think there's not really much to do. I just do Cholesky. And then I'm plotting this. So, oops. So what is this? Well, this is not really going to solve the problem. We need two of these matrices, but actually we don't need the full inverse, right? So here we are going to have many less elements than before. The inverse, remember, it's easy. You just have this, multiply by a vector, and then you get your solution. But you are going to do a lot of operations. All the time you are going to be multiplying. Cholesky on the other side, so you do here back substitution. You start getting variables here. You just back substitute all of them until you get to the top, right? Here, there's still parts that are not are not dense. So even here, we have like some terms that are going to be zero. It's going to be great, and I'm going to explain later how we can get even more zeros. More zeros, less operations, right? And well, we do this, back substitution, forward substitution, and you got it. There's no need to do any dense representation. There's not even need to do all these multiplications, right? So this is the great advantage of Cholesky versus, let's say, normal equation, right? We exploit the fact that actually this is sparse, and we are going to have like things that are not, well, even, no, wait. Here sparsity is not important. Here sparsity doesn't matter. It could be this thing dense, and still this is more efficient, right? This is just a matter of don't invert, just do the things with a proper factorization. With sparsity, it's going to get still better, but when inside you are calling your function solve this linear, all these solvers now, NumPy, they will be using like some sort of Cholesky or maybe QR or something, right? Okay, so let's do a short break, and then later we will keep discussing a little more on QR. Okay, time to get back after the break. Some of you are already discussing. Some of you are how to say, meditating. Some of you are still, you want to see what's happening next, so let's do that. Okay, so we have seen like this thing in practice. Did anyone try to execute Jupyter Notebook? No? Yeah. Yes. It's on lectures. No? In the lectures folder in Canvas? Okay, maybe it's not. Okay, well, you can go home and then try it later if you want. But only one told me that it's not here. What about the others? You didn't check it. After this class, I recommend you to go there, play around, and then you will see what actually all these things mean, right? So what if you change something, if you have more observations, if you have more state variables, what's happening there. Okay, so let's talk about an alternative to Cholesky. In this case, the assumptions here are not that strong. We don't need positive definite. Okay, and for those that don't remember or might need like a quick briefing of what this technique is, basically we have here orthonormal matrix. Right here we have our adjacency matrix, and then what we want is after this, you can think about this as a way of rotating, right? This square matrix. As a result, we are going to get still upper triangular matrix, right? We are going to get something like this. These are things that are not zeros, and then we are going to have a lot of zeros. So the idea is great, right? It's used like in many places, awesome. Well, it has awesome properties. We can also use this as well, right? So let me write like this thing. So this is orthonormal matrix. In this case, Q is square, right? So you can draw the dimensions, but if A is something like this, then Q is going to be something like this. And then here, what we have is this thing. And then a bunch of zeros. Okay, and then we have R to be upper triangular. So this is true for the A matrix. We can factorize into this nice thing, but then we have a little problem. If you remember what we're interested in this, right? We want to solve this system. We know what we can do with back-substitution, so definitely having here upper triangular matrix is going to be useful, but then what about B, right? So the same can happen for B. We just pre-multiply B by the same orthonormal matrix, and then this is going to be kind of rotated or transformed, whatever you want. And then we are going to divide this vector into two parts, right? One of them is going to be, well, there's going to be a lot of zeros there, so you can guess, and the other is going to be called D. But this is a different decomposition. So the question is not really why. The thing is that this factorization is slightly different. If you notice, there's only one upper triangular matrix, right? But then what you need to calculate is this orthonormal matrix and then the upper triangular matrix. While before, for Cholesky, what we had to calculate is only the upper triangular matrix, but in a way that L multiply LT equals your information form. This is another little detail. There's no information form here. So this factorization can be applied to non-square matrices. For Cholesky, that was not true. You need square matrix. Yes? This zero. this is just a result of rotating A, right? So the QR factorization, what it does, it's just changing, well, let's say, components inside this matrix on a way that at the end, you are going to get here a lot of zeros. This is because this matrix, this is still rectangular. That's what I'm writing here, zeros, right? So they are going to be, we can eliminate them. And then you are going to have here an upper triangular matrix like this. Okay, like this, right? So all these things are zeros. I mean, I'm not going to enter on existence of the QR, and I'm sure you have done this before, but it's just for you to know, right? So this is the kind of factorization. And then how is this affecting our algorithm? So let me write it this way. We have, this is the variable that we want to minimize, right? All this norm of this long vector. If we follow this factorization, then we are going to have like different new things, right? The first one is going to be this. Right? So what I'm doing here is multiplying by orthonormal matrix. This doesn't change the norm. So you can multiply this and the norm stays the same. Right? It's just a vector that you are kind of rotating, but you're preserving some properties, and norm is one of them. So this is a good thing. Very convenient, right, from the QR. So we'll have this, and we can still get exactly the same result, so that's why we are equaling. And then I have said that actually this product factorizes into a upper triangular matrix and some zeros, right? So this is going to be multiplied by delta. And then this part here equals these two vectors, right? We are just dividing this into D and E. Right? And then we have the norm of 2. Okay, so far I'm just substituting things, knowing that there's a decomposition that, well, if you want, actually, we can also plot this. So Q multiplied by R equals the matrix, right? So this is originally the QR decomposition. Orthonormal matrices, you can multiply this equals the identity, right? So if you multiply here Q transpose, we get this thing that I'm using in this side. Okay, so very nice factorization. Now, what we can simplify this further, right? So what I can write is, again, this upper triangular matrix, I multiply by D. Here, there's not a subset. Remember that what I'm removing is, I'm removing rows from this R. The number of columns stays the same. So that's why we can just write this R without the zeros. And this is going to be multiplying this vector of unknowns. This is what we want to calculate. This is going to be the subtraction of D. And then we are going to have a vector that there's nothing we can do. It's going to be there, right? So, well, you can bring the gap between, well, we will never solve the problem exactly, right? There's always going to be some observations that are not matching exactly, and there's little errors, actually. This comes from real observations, right? So in this case, this cannot go to 0. This optimization will not go to 0. So then with QR, what we get is this, right? At the end, since this is not important for optimization, we just need to solve for this, right? And this is solved just with one back substitution. Okay, so just an alternative. Note that we don't need We don't need the information form, so we are saving some operations. That's good. Well, depends. And calculating this for dense matrices, actually, it's equivalent to the Cholesky factorization, right? So you can use, I mean, it's not that one is better than the other, right? You get like similar results. One is just calculating one upper triangular matrix and this orthogonal matrix. The other is calculating like this, well, upper triangular matrices. And then there's a question, right? Basically, I'm using R, and before we were using R for the Cholesky. So is R the same as in the Cholesky factorization? Someone who did the linear algebra can answer. Did you study this? No? No? Yes? What? They are not the same. Okay. So, well, it's a question that we are asking, but well, at least from the theoretical point of view, I think, well, I'm going to show now that they should be the same, right? So here we have A. A, remember, that is this. And then if you write it this way, you're going to have something like this, right? And we know that this is the identity. So you know, this is better. So they should be the same. Why? Because if you remember, when we were doing the Cholesky, there's a theorem that says that this solution is unique if the diagonal is positive, right? If you set all the diagonals that were the result of a square root, if you set all of them to be positive, then that means that this should be unique. Okay, I think this is more a curiosity, but it's still interesting how they are related. The problem is that although you find this R, then you need to take care of the B vector, right? So still that's affecting a lot, and this basically means that you still need to do things. But we'll see that there's actually a very interesting property, and you can go back and forth from Cholesky and QR, and well, there's still like there's going to be advantages of knowing this fact, right? That we should be getting something similar. Okay, well, but this is more a curiosity, right? I'm not going to ask you to drive this. Actually, I'm not sure if I'm going to explain it next year. Okay, well, anyway, I think knowledge doesn't hurt. So this is for the QR. Now, if we go to the Jupyter notebook, here what I'm doing is the same, right? I'm just here like, where is the QR solution? Here, yeah, right. So we are just calculating the QR solution of our adjacency matrix. We don't have to calculate the information form. And then we get like a result like this, right? So this is what we were talking about. There's like a upper triangular matrix, a lot of zeros, right? I didn't plot Q, but Q, well, it's orthonormal matrix. Nothing really interesting here. And well, this is what you get. So once you have this R matrix, back substitution, one time, and that's it. Now, let's talk about a little twist on how we solve things, right? This is going to increase also the efficiency by exploring a thing that I have discussed like very briefly, and it's the fact that the information form is diagonal. I mean, the block matrix corresponding to the information form of landmarks is diagonal, right? So if we have that in mind, we can still do some exploitation, right? And in this case, it's called the Schur complement. Well, let's say that the technique, it's called this because this is what it's using. The Schur complement is a different thing. Schur complement for factorization, right? And actually, there's a software out there, right? G2O, which was published by Kumerle and others in 2011, yeah, which is basically, well, one of the contributions. This paper, by the way, is on the readings in Canvas. It should be. And then they explain how they are deriving this. But the sketch of this is shown here. Let's imagine that we have this matrix, this information matrix, and then similarly as what we did for completing this square, we can break this down into different blocks. Here, remember, yeah, this is the information matrix. This is the block that I'm talking about, right? This block is diagonal, right? And this is the thing that we are going to exploit now. This is not diagonal, almost, but it's not really, and definitely not these ones. But if we come here, this term is diagonal. Okay, so this is great. We are going to see what we can do with this. We also are going to divide our vector of improvements or updates into two parts, the one corresponding to X and the one corresponding to landmarks. And then this is the residual, well, the B vector, right? So it's also going to be divided into parts. Okay, so we are just going to break down these things, knowing that this block matrix is diagonal, right? And as you have guessed, well, we are going to exploit this by the Schur complement, so it's going to give us like an advantage. This? Okay. So I'm going to write this. But now with the new divided vectors, right? So with these components. So it's going to look something like this. I need to go down. So from this we have this, and then we have a second part, which is this. You can do this derivation, right? But basically it's taking each of these blocks, and then things are gonna, things are gonna look like this. Right? So we have this now system of equations. What we are gonna do is we multiply by this matrix. Why not? We can multiply everything, right, by this matrix, and then we are going to see what we get, right? So we are going to multiply this term here and this term here, and if we multiply in both and left-hand side and right-hand side of the equality, this is the same, right? So, okay, let's do it. So the first is going to stay the same. Here we are not adding anything. For the second, I'm going to add like this term, that is pre-multiplying both parts. Why am I doing this? Because this inverse is very easy to calculate. The inverse of a diagonal matrix is just the inverse of each of the elements. So that's easy. And then, well, we have here. And then here we have delta xm, delta m minus 1, and now here, right, delta m. Okay, so, well, the first thing that we see is that this simply goes away. as I said, the intuition here is that what we are trying to do is get some sort of Schur complement, right? So that's what I'm multiplying by this thing. And you see that things start looking like this. And then what we are going to do is I'm just going to subtract like one equation. This equation, I'm going to subtract this part, right? And this is the same, so this is whatever, should equal this. If we do a linear combination of both, that's still an equation. Right, so we have this. This is the first part from this first line, and the second for the second line. Okay, here the interesting thing is that since this thing goes away, we have here the information of xm multiplied by delta, and this is exactly the same thing, xm multiplied by delta. So this is great, because this is 0, right? This minus this is going to be 0. And then what we got here is this. Oh, okay. Well, I'm not pre-multiplying, but I should be doing it. Okay, so what we have now is basically we have eliminated one of the variables. We don't have now delta of the landmarks. This is gone, right? Because these things simply cancel out. So when we want to solve this, we just need to solve this part, right? And actually, this thing, this is what we wanted, right? At the beginning, does this look familiar? Is something like the Schur complement? Yes. No? No, it's not the Schur complement. Why not? It's not familiar. Okay, so go back to lecture 3, and there you will see where we get where appear for the first time the Schur complement. But it's always useful when you try to do like inverse, and in this case it's simply like appeared after doing some manipulations. But it's something that is very persistent, keeps appearing in many other places. If not, if you don't see it, it's fine. You don't care. It's just like some manipulations of the matrix, but it's simply Schur complement. The important thing here is that delta m is gone, right? It's just multiplied by 0. I mean, this cancel out. So how is this helping us? Well, first, what you do is we just solve, let's say if we call this thing S, right? We solve S multiplied by this delta x. That should be equal to this new BS. Right, and then the second one is if you want to calculate the solution for landmarks, then you need to go here and calculate this term. So here we'll have this thing calculated. This is known, this is going to be known, so this is going to be like some parameters, and then we are going to have this. Right, so then the increment, it's going to be this. The inverse of this is diagonal. It's very easy to calculate this inverse, and then here what we have is this. Okay, so what we did is some manipulations, but you might not be very convinced that this is useful. Let's see this in action, because I think it's more clear when you see this in action. The idea is that since landmarks are easy to calculate, so since landmarks are not, they don't have the block information, the block information matrix is just a diagonal. It's very easy to invert, right? And then what we can do is just exploit this. So here it is, the Schur complement. You can take a look later at code if you want. This is the information form as we had before. Nothing new, but remember that this block is 0. And the idea is very simple. So if this is 0, if this is a diagonal matrix, what if you just calculate this. Yeah, what if you just calculate this block, which at the end it's going to be equivalent to marginalizing, right? Remember, marginalizing is just taking a block in covariance form, but in information form that's not true. But in information form, actually marginalizing is doing the Schur complement, same as conditioning is Schur complement in covariance form. Anyway, we derived this without talking about Gaussians or information form, and then this is what happens. So we remove this, we do this calculation here of this new matrix, and this new block matrix, this is the previous block minus these terms, right, the inverse, and then we take into account these blocks. If we do this thing here, this is the result, right? It's going to look something like this. So you see that there's a structure. This is still sparse, but the dimensionality has reduced. So here we have like, I don't know, I think 50 points in our trajectory and maybe 50 more landmarks. Here, so this is 100 by 100. Here, this matrix is just 50 by 50, right? And then what we need to do is very simple. So we have this matrix, we calculate Cholesky, and then we do the same thing again, and take into account that this dimensionality has been reduced. So when this thing is useful, imagine that you have a lot of landmarks, which is something that happens with computer vision, right? So you have a lot of features there, thousands, maybe 10 times more than your trajectory, right? So wouldn't it be a good idea just to remove all of them from your estimation? Maybe you don't want to calculate them, or you can calculate them later, right? So with this, you remove them very quickly, and then you just solve the problem by dividing it. First, into this matrix, just calculating your x, your trajectory, and then later, if you want, you calculate the landmarks. Okay, so this sometimes might be a good idea. As I said, the intuition is this. Just break down the problem, knowing that the inverse of a diagonal matrix is very easy. Okay, so let's talk now about the final thing, what else we can do. I have already introduced this a little, but for this I need to do some discussion, but it's simply going to be based on the sparsity, so we want to maintain sparsity. So I'm going to discuss another thing, an extra thing, on top of these decompositions that I have explained, that we can do that will make solving this problem even more efficient, even more. So what is this? Basically, it's ordering. Okay. So ordering of nodes. So the intuition for this, I think, comes more from graph theory, but basically there's an optimal sequence on ordering your nodes that will make the equivalent problem from the linear algebra perspective like sparser, right? So it's not the same removing some nodes at the beginning that removing them at the end. To show this, I'm going to put here an example, as always. Graphical approximations are easy to understand. They are well, they add a lot of information here. Here we have our kind of little factor graph, right? And then, so we have this kind of graph. It's still good. This is still bipartite. Our factors representing distributions are not connected between them, and nodes representing our nodes, in this case letters, are not connected neither, right? Now there's going to be a node that actually is a little well connected, and we'll see what happens with this, right? So right, if I write the information form, right? Remember that it's T. I'm just here, again, making up numbers, so it's just going to be 1 point, same as I did for the information form should look something like this, right? So we are going to have like a diagonal. Oh, let me use a different color. Okay, so this is the diagonal. We always have like connections after doing this multiplication here. And then let me go very quickly. So from A, we should have like some relations which node B with node C, D. What I'm doing here is speed up of the adjacency matrix, right? So I'm just putting here like all the relations that should be there. And I'm also going to assume that this should be symmetric, right? So I'm just writing here like things again. But every connection, everything about it as, well, edges, kind of in these unknown nodes. So A is also connected to E, right? And that's it. So what about B, right? B here, it's just connected to A, so that's good. What about C? C here is just connected to A, so we don't need to add anything else. D, the same. E, on the other hand, it's connected to F as well, right? And then G is connected also to F, right? So just doing this mentally very quickly. You can redo this at home if you want. The adjacency, you could be doing an adjacency and then multiply it, but you will get something like this. You will get elements in all these things. And the reason is always, if you have a relation between a pair of nodes, there should be something. If there's no relation, like in this case, C and G, there should be nothing. As we have defined the problem, there should be a 0 there. So, is it clear? Like, so far the example, well, this is just an example. But the second part of the example is, okay, so we eliminate A, okay? So if we eliminate A, then I'm just going to write the resulting factor. It's going to look like this, B, C, D, E, right? Basically, all these intermediate connections should be preserved. So if we eliminate A, basically B and C were connected directly through A. So if we eliminate it, there should be like a connection. And the same happens for E, the same happens for BD, and the same happens for this. Just so you see that now we have a lot of new, so this is equivalent of just removing one node in our graph, right? We should add all these new observations. We still need to know exactly what they are, right? But for now, don't worry too much. The concept is that these two graphs should be equivalent, right? And after removing this, if we want them to be equivalent, we need to add all these new edges, right, to these nodes. And then here the same, we have F and G, right? So if we do this, and I have this on the nodes, there's going to be a lot of new edges that have just appeared, right? So it's going to look like really, really crowded, like this, E. Just because we have removed a node that is actually very connected, right? So D and then E. Okay, so E here is connected to F. Same goes here, and G, well, this is the same thing, right? Yeah. Okay, so here we see that before we had still like some things that were sparse, but now a lot of new terms are just connecting these new nodes, right? So then the idea behind, and actually this is the whole point of this, is that which factor you are eliminating, which is kind of saying what is the order for calculating your Cholesky factorization, right? It's kind of equivalent. The order matters a lot, right? If you start at the beginning with the most connected node, it's going to have consequences, right? In terms of the information, of the equivalent information, you are going to have something like this. In terms of the graph, you are going to have many well, edges or these factors, node factors here. And in terms of the linear algebra problem, right, what we are going to have is that we are going to have more non-zero elements. And this is what we want to avoid, right? If there's a sparsity, we should be preserving a sparsity also in the transformation, in the factorization, right? So R should be as sparse as we can. Ideally, it should be well, no, a diagonal is not going to be, I mean, that would be a trivial problem, right? But ideally, it should have like almost close to linear elements, right? Imagine a diagonal with some things later. If you have a lot of elements there that are actually not necessary, maybe the order can help. Maybe you have done an order that is not as correct as it should be, right? So, yes. I mentioned back substitution for solving your problem. Yes. Exactly, yes. When we do back substitution, we want as many zeros as we can, right? No, it's after. Back substitution, it's after. Once you have your factorization, right, then you do the two substitutions, back substitution and forward substitution. No, it's an equivalent way of taking a look at this, and I'm going to show it later with the Jupyter notebook, right? So this motivation, it's easily explained with graphs. It's very complicated to explain this with Cholesky factorization, right? How the order affects but it's very easy because all these things are related. Graphs and the factorizations, right? It's, you can imagine this as two things that have a very tight connection, right? So what affects one of them is also affecting the other. In this case, the number of edges or this kind of information form after multiplying to adjacency matrix, it's going to be denser. This translated to the Cholesky factorization, it's going to have the same effect. It's going to have like more elements that you need to take into account. Why? Because if you remember, the Cholesky factorization, it's a block iterative process where you just keep whatever you had done before to the next steps. If you have already, right, something like this, like this, or I don't know, well, if you already have here like a vector here that has a lot of non-zeros, then for the next steps, this is going to affect you, right? So what's the ideal thing? That this to be as few elements as possible, right? If you do it this way, then your Cholesky is going to be sparse. But it's better explain this in terms of graphs. That's what I'm doing this thing. So in graphs is you remove one graph, you remove one node, and then what is the consequences to have the same thing. In terms of Cholesky, it's the other way around. So you have diagonalized, I mean you have factorized like one of the elements, you have like a lot of zeros and some elements, but still you need to take into account this to the other part of the variables, right? So how this is affecting, it's equivalent to this. There's going to be more elements. Is this clear for everyone? I'm going to show very soon the resultant matrices, but okay, so then if this is true, what can we do? There's many, well, ideally what we want is the optimum ordering, right? Who wants the optimum ordering? You don't want? Okay, bad news. The optimum ordering is NP-hard. So it might be harder to find the optimum ordering than actually solving Cholesky. But there's still a lot of heuristics and simple tricks that we can do, right? And on this, there's a lot of things on the literature, right? How to do like heuristics, orderings, whatever, right? I'm going to explain like a couple of them, like very quickly. Minimum order degree. Okay, so the intuition. We want to start eliminating those nodes that have fewer connections, right? I think you have seen what happens when we eliminate a node that has a lot of connections, right? A lot of edges around. So the intuition is going to be first, nodes with fewer edges. Oh, we even have like soundtrack. That's okay. Okay, so everybody agrees? Is this like a good thing to start with, right? Let's eliminate those. Why? Because we have seen that those that have high number of edges are going to be problematic, right? This is going to result in more elements here. So, so then I'm going to start with a very simple heuristic. We are going to permute nodes, like, for instance, in order of number of edges, right? And this is very simple heuristic. This is not really a good approach, but it's still going to be useful, right? There's other algorithms that can be used here. And why is the reason for that? Because if you do that, then the matrix in terms of the information form or the number of zeros that you have on your Cholesky is going to be like much sparser, right? Okay, so there's like several routines for this. We have called permutation, called perm, right? So you can use this for Cholesky, well, for information matrix, right? You also have like call permutations, not for square matrices, but for rectangular matrices. So in this case, we want this for Cholesky, and in this case, we'll want this for QR, right? You will see, but we can start with this very simple heuristic, right? So what I did is here there's some code. I start just by looking at the mean, right? This thing. I'm just sorting by number of edges. Very stupid, nothing else. Again, this is not a good permutation algorithm if you have like very large scale, but this is going to help, right? For this, later I'm going to cite like a couple of proper algorithms. Still, they are heuristics, right? And the optimum on this ordering is very hard to calculate in general. So, well, we do this, we permutate our adjacency matrix, and if this is the this is how it looks, the permuted information matrix. So here what I'm doing is, well, permuting, counting the number of neighbors, number of edges, and it looks kind of similar as before, right? Let me put it before. So what I'm doing here is Cholesky. This is it. So this, if you permutate it, here on the top left, what I have is less connections, and here I have more. So if you permutate this thing, you have exactly the same information matrix, simply reordering things. Okay? I've done this. I mean, you can check code if you want, but it's the same one. So then what's the yes?
What do you mean by the same? You see that you have the diagonal sum of blocks?
You have the same values. They are simply permuted, right? So rows and columns, but it's exactly the same matrix, the same information matrix that it's here. It's this same information matrix. This is just permuted based on the number of elements that is for each node, right? So here, what I have is nodes with less connections. You see here, for instance, this guy only has, I think, 1 and 2. I think this has 3, I don't remember. Maybe here you have some with 4, 5, 6, depends, right? So this is basically some landmarks were observed more times than others, right? But it's the same thing. You just shuffle things and you get exactly this matrix. Okay, and now this is the result. So this is the Cholesky factorization of this new matrix, right? If you see, it has not so many non-zero elements, right? There's a lot of zeros here, a lot of them. In fact, we only have 400 elements While if you go here to the Cholesky, yeah, we have 3,000, right? And the only thing that has changed here is the ordering. Again, this is not a good ordering strategy. This is the most stupid one that you can imagine. Start with those, start just counting number of edges, right? Okay, thumbs up. You see the great advantage of ordering things. Do you believe, would you, if it's free, I mean, if it doesn't mean time for you to implement, would you be using this? Well, there's always laziness, right? Of say, yeah, who cares? I'm just going to call the routine and invert the matrix, which you can do. But you know that you will not be doing best as you can. Okay, so this is for Cholesky. The same goes for the QR factorization. Here, this is the permutation of A. Right now, since, well, this is not a square matrix, I'm permuting slightly different. Basically, it's based on the number of columns, right? So with this, basically, it's saying like how many times you have like connections here. Well, whatever we had before, remember there was like some structure. This is gone. It should look bad, but in terms of then what you get here is this factorization, right? You still have like very few non-zero elements, right? So this is good. We have removed like numbers that later for back substitution are not going to be used, right? So, yep. Yes, 1 minute. 1 minute and we'll be finished. And what about the Schur complement? For the Schur complement, it's the same, right? I can come here and, so this is the information form after doing the Schur complement. You remember removing the part on the block X, removing cross terms, right? So it looks something like this. It's still nice, right? But this is not the best thing you can do if later you want to do like some factorization. Remember, it's almost equivalent, right? Thinking on the graph part and thinking on the linear algebra factorization. So it's kind of the same thing. Ordering here, what it's telling you is like which variables are going to be affecting later, and for the graph is like kind of number of edges. So then this is permuted thing. I'm not sure why, but well, basically yes, here we have more nodes, more connections here than here, right? In this, basically we have less. I think this is 2, 3, well, I don't know. The machine did it, I didn't did it. And then the factorization is the same, right? So you get less zeros, which is good. This is something you are looking for, especially when you have large scale problems. And well, basically, yeah, here there's nothing else. Let's get back to here. If I said that just ordering it's kind of a trivial strategy, useful but kind of trivial, then you have like more proper algorithms. Like for instance, here you have the, well, column, right? So this is again an heuristic. But still, you get like very good results. So this was published by Davis in 2001. And the other is the minimum order degree, I think, which is also implemented somewhere. I think many other libraries like Eigen uses this. And well, basically this is it, right? So this is the best we can do. Well, maybe you can do more. But so far in this paper, this is what the authors have reported, right? This improves a lot the problem, the solution of the problem. Now, you don't really need to do the inversion, so the complexity is not O square. Right, but we are going to have something that might be close to squared, right? Because there's still, if everything, well, yeah, on bounds, I'm not going to write here anything, because on the worst case, it's still going to be cubic. But I think everyone agrees that in normal conditions, in usual cases, although there's no guarantees for this sparsity solves, I mean, is a great improvement on the efficiency of calculating this solution, right? So now, every time that you have like this kind of problem, you can say, okay, I'm just going to call these routines and do this. If you call like modern linear algebra libraries, under the hood, they might be doing something like this, a variant of this already, right? But now you know. You could also be implementing this for problem set 3. This time I didn't ask you to implement, except if you want to get more points. Then you are going to be doing back-substitution. But in general, no, the solution is just going to be, okay, just call your inverse function, linear square solver, whatever you want, and then you will solve it. Okay, so with this, I hope I have convinced you that we have maintained the best of both worlds. We have the full trajectory, gives us best estimate for nonlinear, best way of estimating our state for nonlinear systems, and at the same time, this is still very efficient, right? Barely not as efficient as filtering. With that, it's very hard to compete, but some of the problems of filtering are not here, right? And still, the computational efficiency is very high. Okay, so thank you. I think that was it for today. Next lecture is going to be on Monday, right? I'm going to talk a little more about other cool things that we can do about this, and I'm going to talk about post-SLAM, which is no landmarks, just trajectories. Okay.